Hi everyone, thank you for coming. Today we're lucky to have Eric Jonas coming from Berkeley. He got his bachelor's and master's in EECS from MIT before starting a PhD in neuroscience, advised by Matthew Wilson and Josh Tenenbaum. During his PhD, he became interested in predictive databases, at which time he started to do a startup. He did that for a couple of years, and it was eventually acquired by Salesforce, at which time he became the leader of their ML team. He did that for a little over a year before deciding he wanted to go back to academia, and did his startup postdoc with Ben Recht at Berkeley, where he's been ever since, working on a variety of different science applications with machine learning tools and systems, and we're all very excited to hear about it. So let's welcome Eric.
Thank you, Kevin. Is this on? Great. So the moment I decided to actually do a postdoc, I was in the car with Ben Recht, my PI, and Kevin, and we were driving up to the AmpLab retreat. They have this kind of biannual giant retreat. And so Kevin was literally there at the moment when I said, all right, I guess I'm actually going back into academia. And it was a wonderful decision. Very, very lucky to have had the chance to work on what I'm going to talk to you about today. So I believe that the most interesting and exciting results in science over the next 30 years are going to be driven by advances in computation. And what do I mean by computation? So I think we can take kind of a fairly broad perspective on computation here, right? I think that there's ample opportunities for advances in modeling, right? In kind of trying to capture our intuition, our prior knowledge about problems, and formalize that knowledge using the tools of computer science to better understand kind of scientific applications. I believe there's tremendous progress underway and that will continue to take place in the realm of inference. That is, in kind of bringing modeling and data in contact with each other and trying to make interesting queries about systems under study. But I also think there's tremendous opportunity here in scale. And we talk about scale, we don't just mean kind of scalable computation, but we're also increasingly talking about the scale of data that we have access to or that sometimes we have to deal with. And these are, of course, all closely interrelated. And I'd love to kind of talk about all of them, but I think that all of you would eventually get a little tired with a 7-hour talk. So today I'm mostly going to talk about this inference part here. But first I'd like to touch at least a little bit on some of the work that we've done on the modeling and scale sides, right? I come from a background where modeling is taken very seriously. When Kevin alluded to me doing my PhD with Josh, we were very interested in building kind of structured probabilistic models. And often when you say models, people have very different ideas of what models are, right? In science, especially in physics, we often think of our models of the physical world as looking like this, so, from electrodynamics or from GR, kind of fairly compact, parsimonious representations of reality that distill what really matters and ultimately lets us kind of make predictions. But increasingly, our models look like this. So this is one of several climate models, or the schematic, the rough block diagram of one of several climate models from this amazing poster that was presented at the American Geophysical Union annual meeting in 2011, showing how all the differing parts of the Earth and the atmosphere and the ocean system interact for future climate activities. Now, of course, we all know climate change is a real problem, and we're potentially making kind of planet-scale decisions around these sorts of models. But these models look very different from the physics models I was just showing you earlier. This is an expression of the number of lines of code in each of these models, and that x-axis there is in thousands of lines of code. So we're talking about models upon which we're making kind of fundamental decisions about the fate of the planet that are kind of as complicated as modern software packages, right? So this is very different from what we're used to, and I think really serves to highlight the crucial role that kind of all parts of computer science will play in the coming model-based future. But we also have models to try and understand what's going on in complicated systems where we don't know very much, right? So this is a model that we fit to some neural data, where in biology we often have this problem where the systems are incredibly complicated, they're incredibly nonlinear, and we don't really understand what's going on behind the scenes. We want to capture some of that intuition. And nowhere is this more apparent than in neuroscience. So in 2013, the Obama administration announced the formation of the Brain Initiative, right? And from the position paper there, they said, the goal of this brain initiative, the goal of the resulting brain activity map project is going to be at reconstructing the full record of neural activity across these systems, because we'd like to understand what these systems are doing. But immediately you run into this problem. How do we build models to understand complicated systems where we don't really understand how those systems work at all yet, even in the presence of all of this data? So we had this idea, maybe we should take a model system that we do understand, right? In our case, we took a classic microprocessor, the MOS 6502. Now, the beauty of taking systems like this and kind of taking a computer science view of reverse engineering these sorts of systems is that as computer scientists, we know how this system works, from a device physics level all the way up to a rich theory of computational complexity. And we can have this system engage in what we might call naturalistic behaviors, right? Play the resulting games, and watch the activity of every transistor on that chip. And we can even imagine trying to apply some of the neuroscience techniques that we've been using in neuroscience to reverse engineer biological systems and try and understand what's going on inside the system. But our takeaway from this work, which received, I guess I might say, a fair amount of attention, was that the models that we're using in neuroscience are kind of really impoverished right now when it comes to understanding how computing systems work, right? And if they can't work on something as simple as a microprocessor, maybe what we really need are fundamentally better or more powerful models, right? So it's not just enough to have all of the data. We need to be thinking more seriously about these models. And of course, we've done some work on this. We have collaborators who have done some work on this. There's some people here at UW whose work has actually been very kind of crucial and inspiring in this space. Here we were trying to kind of reverse engineer some of these connectivity diagrams. I'm happy to talk about this at some point, but it's not really what I want to focus on today. I just want to stress that kind of the need for modeling and for modeling at scale is crucial, right? And we're trying to make progress there. Let's talk about the scale side of things, right? Many of you have seen nightmare graphs like this, or I don't know if you're not waking up in the middle of the night screaming about this, then maybe we have different hobbies. But there was this lovely period here during the 90s in which kind of music in Seattle was ascendant and processor improvements were equally impressive. And now we're in this regime over here, right, where kind of our clock cycles are not getting shorter, our transistor density is no longer going up where we wanted it to. And so not only do we have tremendous compute available, but in some sense that compute is becoming more and more precious, right? So taking advantage of scale means taking advantage of efficiency as well. And we found that, you know, in the AMP lab, where Kevin and I were, kind of half of the graduate students in machine learning had never run one of these big data jobs or had never successfully used a big data platform. And we're like the people who built Spark, right? You'd think that we would be good at this. And to us, this was kind of somewhat of a damning indictment, but it really didn't click until we were giving a computational imaging seminar explaining how cloud computing works, and one of the professors asked, well, why is there no cloud button? And of course we said, well, that's a dumb question, like the cloud is complicated. It could never be a button. But the more we thought about this, the more we realized this was actually a pretty compelling question, especially when you wanted to know, how do we bring the benefits of this kind of scale to a larger audience? Right? So we built a system called Pyren, which basically just lets you transparently map any function over some collection of data. Right? So you write your function in Python, you map it, you get the results, and surprise, the results come back. But what's happening behind the scenes is your data is being kind of transparently marshaled to run on a very large number of cloud machines using this new infrastructure developed by Amazon that goes by the name of serverless compute technology. Why is this interesting? Why am I up here pitching just the map half of MapReduce? Well, these serverless platforms give you literally thousands of cores just sitting there waiting for you to command on kind of tens of milliseconds of time scale, right? So there's this tremendous potential here to very rapidly be able to take advantage of this scale and then just as rapidly be done with it, right? These sorts of serverless platforms are a great example of kind of the scaling opportunities available when you start trying to think about novel places to push data science, right? So dwelling on this just for a second, they let you run these short functions without worrying about infrastructure. But there are some real limitations. You only can run a function for up to 15 minutes. You only have a few gigs of RAM. The model from Amazon, this is from Amazon promotional material, was that you could write your little function here, and then people would say upload images to your website. It would do something and stick the results in a database, right? The idea of having these tiny little tasks that were completely independent. And this here, the dollar amount goes up proportional to the amount that you're using it, right? You're only billed for the time you use. So Jeff Bezos, who I assume that's who this is here, looks happy the more you're using it. But the appeal here is that this is a piece of computing infrastructure that was designed for this kind of trivial application that we discovered we can actually co-opt for very large-scale data analytics. And in fact, competing cloud providers also have these sorts of platforms. Other people now have used this infrastructure that we've built kind of across different scientific domains to do large-scale analytics from their laptop without really worrying about any of the headaches that you traditionally think about with these large-scale distributed computing platforms. And you say, well, Eric, that's great, but how does this fit into the larger cloud ecosystem? And well, 10 years ago, almost to the day, people at Berkeley wrote this paper called Above the Clouds, where they said, this is the direction we think cloud computing is going to go. And recently, last week, we put out this paper where we're arguing that these serverless platforms are actually going to be kind of the fundamental computing primitive that we're all going to be taking advantage of over the next 10 years. Unless you say, well, but Eric, I can only do so much with map. You say, well, of course. But in fact, you can use these things coupled with large-scale kind of storage infrastructure that the cloud providers are producing to do radically different things. So in this case, we built this package called NumPyRen, where the goal is to do very large-scale linear algebra, right, using these serverless platforms more efficiently than you can do with existing infrastructure, like MPI. And so in terms of core seconds of efficiency here, this is the y-axis here is in log units, and we see that we're able to do substantially better, taking advantage of these cloud providers' infrastructure's ability to kind of quickly scale up and scale back down. But I'm not going to talk about that today.
Lower bound mean there?
Huh?
What is the theoretical lower bound mean?
Just total number of ops divided by the individual rate at which a single core can calculate that op, right? So in some sense, both of these reflect some degree of fundamental communications overhead, right? That's what we're trying to capture. But I'm not really going to talk about this. I really want to focus on this inference part, because I think this is one of the most exciting places to be doing computer science right now. When I say inference, what I'm talking about is kind of, as I alluded to earlier, this process of bringing data into contact with some sort of model and running an algorithm that lets us then ask interesting queries, right? Now let's talk about the modeling part. Now if you're a machine learning person, right, you might say, what model? I really want to design a network or some sort of function approximator, and maybe I don't necessarily care very much how closely that maps to the generative process that gave rise to the data, right? A ResNet is a very powerful system for classifying images, but we don't necessarily think that all of vision can be explained by these nested 3x3 convolutions. If you're a statistician, you might be constructing models that capture some aspect of the generative process, and maybe you really believe that model, but you know that it's just an approximation. Today, I'm mostly going to talk about going even further in that direction of believing your model, to what are called kind of inverse problems, where you completely trust the forward generative process that gave rise to your data, right? So what is an inverse problem? So if you're a double E person, you can kind of go to sleep for the next few minutes. But I often find many of my computer science colleagues haven't really thought too much about kind of the fun challenges that live in inverse problems. See, when we talk about an inverse problem, we mean that there's probably some system, right, that we would like to know something about. Let's call that X. And that system propagates through some forward model, through some measurement process here, f of x, ultimately giving rise to some data. And so we have this model for observing the universe where epsilon is maybe some sort of noise. And we'd like to go in the opposite direction, but this forward model is crucially very well understood. So the inverse problem is just inverting, going from y back to x. And these problems basically define all of the interesting scientific measurement modalities that we're familiar with, right? So adaptive optics is this nice example of an inverse problem where what you're trying to do is in real time deconvolve aberrations in the atmosphere such that ground-based telescopes can see as well as space-based telescopes. Super resolution microscopy is this great inverse problem where we're trying to see cellular structures smaller than the wavelength of light by cleverly making measurements. All of tomography, ranging from kind of MRI to CT, to even kind of measurements of what's going on underneath the Earth, are inverse problems. And in fact, where a lot of the classical motivation has come from. But even phase contrast microscopy. So I always like this one because you might not know this if you've not spent a lot of time in a wet lab, but cells are actually transparent, right? But by cleverly measuring things and kind of encoding our measurements, we're able to actually measure the optical path length. We can use inverse problem math to make things that are literally invisible visible. And of course, notions of these problems being interesting goes back to questions originally posed by Weil, and then kind of Mark Koch put best in this great paper from the middle of the last century asking, could you hear the shape of a drum? That is, if you had a drum with some external geometry and you hit it with a mallet or you excited it, could you infer that geometry? These problems have kind of driven a lot of, I would argue, applied mathematics and computer science over the past century. And let's talk about why they're hard, right? Inverse problems are hard for exactly the same reasons that inverting a matrix is hard. I gave this talk to some physicists recently, and they were like, inverting a matrix isn't hard. And I was like, all right, bear with me. If we imagine that we just had a linear inverse problem, why might solving this, why might uniquely determining x from observations y be hard? Well, if A is the identity, this is quite easy, right? But if A is not full rank, or if A has poor condition number, right? That is, if the ratio of the maximum to minimum singular value is huge, solving this can be very difficult. The problem can end up being very ill-posed, right? But you can often get around this by exploiting some sort of prior knowledge. You start to see why I call my startup that. So how might we solve one of these problems? Well, I was trained as a Bayesian. I'm not sure I should be admitting that in public. But I very much started off thinking of the world in this very probabilistic formulation. I'm going to write down this full generative probabilistic model and then kind of try and condition on the observed y and make inferences about x. You can do that in a lot of ways. You can guess and check, right? Which of course sounds insane, but of the basis of rejection sampling. And of course, there was this whole area of approximate Bayesian computation that was really hot like 10 years ago. You can use kind of all of your Bayesian inference machinery, ranging from sampling methods to variational methods, to try and solve these sorts of problems. But often for the kinds of inverse problems that we're interested in, these methods don't tend to work terribly well. And so I wanted to work with Ben specifically because I wanted to really understand how to solve these sorts of inverse problems from an optimization perspective, right? And this actually ends up being what your MRI machine does every time you go to the doctor. Well, hopefully you're not getting an MRI every time you go to the doctor. But when you go and get an MRI, conditioned on that, somewhere in there, there's a least squares model with regularization that's being fit. And you can fit this with kind of all of our standard techniques, right? Projection methods, splitting methods. Today I'm going to talk about kind of a fourth weird way of doing this, which is just trying to directly approximate that inverse function, right? We've gotten very good at building powerful function approximators over the past 10 years. And let's see if we can use those to kind of elucidate interesting inverse problems, to understand what's causing this data. Now, of course, I'm not the first person to suggest we use deep learning for inverse problems. If you look at Google Scholar, there's a lot of hits. But one of the challenges with a lot of these existing approaches is that what they're trying to really learn from data is that regularizer term, right? So they're trying to figure out a good model directly from data. And I would argue that's a little bit dangerous, especially for some of the applications that we're talking about. Every episode of SVU inevitably involves someone trying to enhance an 8-pixel image beyond what is reasonable. And in fact, there was this great paper from Google Brain a few years ago where they did this lovely job of training what we now kind of recognize as well within the scope of using a GAN to go from a small number of pixels to a real image. And often they kind of look similar, right? I'm sure if you did that with kind of today's technology, it would look even more impressive. But the reality here is that we're basically hallucinating sources that just happen to match with our data. So there's this interesting question, right? How do we make this trade-off between really understanding what gave rise to our data and using kind of priors that we believe in and just hallucinating things that might happen to fit? And maybe this is okay for computational photography applications, right? Maybe you don't necessarily care if your face on Instagram looks just right or not. But for a lot of the medical and scientific applications we care about, where you want to make subsequent downstream measurements, this is very important. So we got interested in this space of what I'll call structured prediction, right? Or what is called structured prediction. See, when we teach machine learning to undergrads, we often focus on problems of classification or regression. But for our inverse problems colleagues, they often think carefully about trying to recover vectors of in Rn or images or collections of voxels, and often think about their priors in terms of just things being sparse. But there's a whole interesting structured universe out there where maybe what we're trying to estimate are the state transitions in some sort of latent variable model, right? Or parse trees for NLP, or point sets, or even graphs. And of course, these problems are not new, right? There's lovely work on kernel methods for this from 10 years ago. And of course, there's the modern deep learning view of a lot of these approaches. But I was interested in, is it possible to apply these techniques for structured inverse problems? And so I'm going to focus on two of these problems today. One is super resolution microscopy, and the other is chemical spectroscopy. Now, for people who saw my talk in, I think it was October, maybe November here, my apologies, because a lot of this is going to be similar, except the results are all now better. But Kevin assured me that was OK. So showing some more material, not the results being better. I hope that's OK with everyone. But the interesting part here is that I think the approach that we're outlining, I think, is applicable to a lot of different application domains. So let's start with the super resolution microscopy one. See, microscopy is an inverse problem, right? You have some system, in this case, some set of cells on a slide. You're going to propagate it through some forward model, which is optics, which is basically a linear optical system. If you haven't read Hecht's optics book, I highly recommend it. It's a lovely read. And at the end of the day, you get a collection of pixels. And you'd like to, from that collection of pixels, infer something about what was on that microscope slide. But of course, here, if your graduate student built the microscope properly, the problem is easy. This is just the identity matrix. Literally, the thing you're looking for has appeared on that collection of pixels, right? This is how most of optics has worked for a very long time. But there are challenges in a lot of these optical systems. There are fundamental physical limits. Every optical system has an impulse response. In optics, we call it the point spread function. This means no matter how small of an input source you have, the output will always have some kind of finite dimension, right? Some finite width. It's the amount that a point will spread out. And this arises from the fundamental wave nature of light, right? And this really limits your ability to resolve 2 points as they get closer and closer together. This is known as the Abbe diffraction limit. And it's proportional. Your ability to resolve 2 points is proportional to the wavelength of your measurement system. And you say, but Eric, light's really small. Surely that's OK. But you know, there's a lot of interesting biology happening below the wavelength of light. And so what you'd like to be able to do is resolve that. Now, what if we get really clever? And by we, I mean various optical physics collaborators and colleagues. And you replace your traditional microscope with a complicated piece of equipment built by a very industrious graduate student. And that microscope encodes the information in such a way that you can use some algorithm to decode it and see what you were looking for. If you Google image search for algorithm, this is like the third thing that comes up. So I assume it's a very good algorithm. This technique is known as super resolution microscopy, or stochastic optical reconstruction microscopy, and won the Nobel Prize in 2014. And the idea here is as follows. If you'd like to resolve something like, say, this E with very narrow lines, and your point spread function is finite, you can imagine if you just tried to directly image it, right, you would get a mess. But if instead you could turn on individual points of light on that source, as follows, and then localize their centers, you could actually build up a map of each of those centers, right? We can fit a Gaussian. That's a thing that I think most of us know how to do in machine learning. And ultimately recover the smaller, below wavelength shaped or sized object, right? This is the idea behind this class of microscopy. And you can even go further than that. So a few years ago, people had the idea that what if you make that point spread function also encodes something about z, about the z direction from the focal plane, right? So the point spread function, the further away the point source is, the more it's going to change its geometry, right? In the double helix one, it rotates. It's these two bubbles that rotate. In the astigmatic one, it elongates in a different direction. That means that with a single shot, you can resolve both the 2D and the 3D location of each of these emitters, or these fluorophores. So we're going to structure our problem as follows. We're going to have some input image here, right, which is going to be a collection of those point sources at various x, y's, and z's. We're going to use a deep network that we call deep loco to then recover the explicit locations in x, y, and z, as well as their intensity. It's called deep loco ostensibly because we're localizing points, but the reality is that Ben thought we were crazy for trying to do this. But we're going to train it entirely on a physical simulator, right? We're going to take a simulator that uses physics and that, in fact, tries to be relatively accurate and generate arbitrary amounts of synthetic data and try and then recover this sparse point set. Now, why do this, right? One reason is that if you have a fully feed-forward method, it might be very, very fast. This might actually let you start to do real-time imaging at the megapixels that you've been wanting to do. And we find that, in fact, compared to kind of the existing best-in-class algorithms, we're capable of doing about 20,000 frames per second versus existing methods that are on the order of tens or less, right? While not losing any performance and, in fact, gaining some. Now, this is interesting, but there's this question. We're kind of trying to recover these discrete point sets, right? Are these 2 point sets the same, right? So we have single scalar dimension here, x, and their weight. Now, obviously, I wouldn't show them to you if they weren't, because it would be kind of a trick. But it's much easier to see when you render them into some image, right, that actually they're the same. It's easier to tell 2 images apart than 2 lists of points. You've removed this permutation of variance by effectively projecting into a higher dimensional space. So if we think carefully about our image generation process here, right, we have some estimated collection of points gamma. And we have the true collection of points, or gamma hat, and we have the true collection of points gamma. You'll note that they're indexed by different different letters, because there could be different numbers, right? We might not recover all of the true number of points. We're going to go through this kind of fictional image generation process, where we're going to kind of take those points and convolve them with some little kernel here, right? So this is a nice little Gaussian bump. And we're going to take the resulting images that we get and compute the L2 distance, right? Nice and easy. Now, the challenge here, though, is that this is super resolution microscopy. What does that mean? One is we're trying to resolve the location of these points far below the size of one of our pixels, right? So we'd have to grid incredibly high. But also, we're trying to do 3-dimensional recovery, so we'd have to grid in 3 dimensions. Well, we can recognize here that, in fact, this loss function, right, is actually the difference in this collection of atoms here, right, these collection of these sparse points. And we can do this quadratic expansion and find that there's this nice kind of resulting PSD function here that just depends on the difference between any 2 of these points in our source, right? We can basically compute this matrix. And this becomes very efficient for small numbers of points, right? And we're often talking about recovering kind of in an order of low hundreds of points per image, right? So we can very easily compute this. And as a result, we can assemble these pieces as follows. We take some true collection of points. We pass it through a simulator. We get some fake image. We have a deep network. We have it output some collection of points. And we use this kernelized loss function here, right, that really just depends upon the differences in those point locations to do recovery. Excuse me, I think I'm allergic to Seattle a little bit. So in doing that, we can then train the network. How well do we do? Well, we tie our existing, so one of the challenges when doing any of these sort of methodological developments is that you always want to compare to, the real thing you should do is compare to the existing best in class. And a great way of doing that is collaborating with the people who wrote those. So our two-dimensional comparison is going to be with this method ADCG, which won the Super Resolution Microscopy Localization Challenge in 2015. And we find that our method, the deep loco, performs kind of just as well as you vary the point density, as you vary the source density, kind of across all these things. Obviously, I'm showing you that we do quite as well. And if you want the exact details, you can look in the paper. But also, we do even better than the best-in-class 3-dimensional localization method, right? So up here is our recovery in x and y and in z and x. And this is spliner, the kind of existing method that people are using. And these are kind of the metrics where we're using kind of how closely did we match the correct points, right? This is joint with Hayes and Babcock, who wrote spliner. But again, because we've basically trained a forward network to do this, we can be kind of dramatically faster. And I think that ends up being the interesting point here, right? This may have been crazy as a start, but the idea of kind of directly learning an inverse function for some sort of like sparse structured set is possible, right? And this ended up being very encouraging, right? I think that the part that really surprised us was that our performance ended up being on par and our runtime was dramatically faster. But the real reason why this is interesting, or one of the things that makes us most excited, and this is ongoing work, is that we can imagine incorporating substantially more complicated forward models into our recovery process. That is, systems with greater degrees of nonlinearity, systems with higher noise, systems with greater aberration. And in some sense, you can think of this as being a little bit like the poor man's probabilistic programming. Right? So when I was in Josh's lab, we spent a lot of time trying to build probabilistic programming systems that would do general purpose Bayesian inference. Turns out that's very hard. It's still, years later, an active area of research. But it's fairly easy to talk to a physics graduate student and say, if you can write down a forward simulator, which most of them can do, our existing function approximation technology is kind of powerful enough to start directly inverting these sorts of problems. And this led us to think that maybe there were more interesting structured sets we could try and recover. And that's where we get to spectroscopy.
How robust are they to distributional? Like in these imaging studies, presumably you care about distributional shift because they're using it for sciences.
Yes. So we talk about that in our paper. They tend to be very robust, and in fact, all of the numerical results that we have in our paper are from this contest data set, which is it has nothing to do with our simulator at all, right? So a real challenge here is that, if you're writing a simulator and then validating your method against your simulator, it's great, you get a cookie, but like it doesn't necessarily reflect how it's going to account for the fact that the distribution that your simulator is giving you might look different from the real world, right? So we find it to be very robust, especially if we do kind of the obvious things like train on differing levels of noise and kind of properly check for that. There will always be things that we can't kind of accommodate, but at least in the initial work, we haven't found any kind of obvious roadblocks. Does that answer your question, Sean? But great. So then we started thinking about spectroscopy. And I say we started thinking about, but the truth here is I've been thinking about spectroscopy for a very, very long time. If you like physics and if you like electromagnetism, spectroscopy is the place to be. So fundamentally, spectroscopy is about kind of understanding how electromagnetic radiation interacts with matter. This diagram here in the back is actually the absorption spectrograph of sunlight as it passes through the atmosphere. And you'll note that on each of these vertical lines here actually represents a different energy of interaction between some photon and some set of electrons in an atom, right? But the beauty here is that what I'm showing you here is a continuous varying of wavelength with very discrete readouts, right? Spectroscopy represents this kind of beautiful opportunity to really get at the fundamentally discrete or quantized nature of matter and to learn a lot, right? So spectroscopy has a beautiful history ranging from early astronomical spectrographs that determined that there was some element on the sun that we hadn't really seen here on Earth. They called it helios. We now know of it as helium. To elucidating the structure of chemicals in your organic chemistry class, for those of you who have, like me, suffered through perhaps too many years of organic chemistry. To understanding what rocks are made of on faraway planets, to determining the structure of proteins, to even violating your civil liberties at the airport and attempting to detect kind of errant substances. And I would argue that spectroscopy is made for computer science, right? A lot of the original work done in chemistry, in the mathematics of chemistry, were done by people like Cayley and Sylvester, right? Because molecules are fundamentally kind of edge-weighted, colored, degree-constrained connected graphs. These are things that we know of from our undergraduate data structures classes, right? And in fact, I love this quote here. This is from a paper that Sylvester published in Nature, where he introduced the term graph into the lexicon and attempted to describe these molecular structures that he's seeing. But spectroscopy, I would argue, is also made for machine learning, right? So one of the first expert systems ever built was this Dendral project at Stanford. And the goal there was using mass spectroscopy to kind of understand the structure of molecules. And in the final retrospective written in 1987, they said, the elementary problem of inferring composition from molecular mass now well solved. Could we take the next step? Model the chemist's inferential procedure in finding the structure from the spectrum. And that's what we're going to talk about today. Now, there are many different types of spectroscopy, right? Because there's many different wavelengths of electromagnetic radiation. We're mostly going to focus on this technique called nuclear magnetic resonance spectroscopy, or NMR, right? So for those of you who have, again, suffered through organic chemistry, now you can go to sleep. Don't worry, everyone gets a nap. But NMR works by taking some molecule, placing it inside of a very powerful magnet, right? So this is this external B0 field here, and irradiating it with RF energy. When you do this, each of those nuclei, in particular the carbons and the hydrogens, will resonate with distinct frequencies. And those frequencies will reflect something of their local environment. It's a little quantum mechanical readout about what's happening at the atomic level. So let's take a popular recreational drug. Here you can see that the hydrogen spectrograph reflects kind of 3 different equivalent classes of hydrogens, right? Which tell you something about their local bonding structure. Now, why focus on NMR? For starters, it's an incredibly precise technique. Those line widths that you measure out, the resonance frequencies, are incredibly narrow, very high Q, which means you get a lot of bits per measurement. It's an extremely robust and mature technique, right? Most of the physics was worked out in the latter half of the last century. It's signal and noise ratio limited. Now, why is that a good thing? Well, it's not. But what this means is that often many NMR measurements take place by making kind of the same measurement over and over and over again. So as computer scientists, we think that immediately might suggest that there are more clever ways to make some of these measurements than just kind of blindly averaging. It's fairly turnkey. An undergrad can build a reasonable approximation of an NMR spectrometer in a semester. And the underlying dynamics are fundamentally quantum mechanical. So we're mostly going to focus on chemical shift resonances today. But in fact, what's really happening is you're exciting this quantum mechanical system of kind of coupled systems of coherence. In fact, my advisor, Ben Recht, spent part of graduate school trying to use liquid state NMR to do quantum computing on molecules. So the dynamics are very rich. We're going to structure the problem as follows. We're going to start with the molecular composition of some molecule and its spectrum. And we would like to recover its molecular structure. Right? So from a computer science perspective, we're going to start with a collection of vertices and per vertex properties. And we're going to try and infer the edges here. Right? Now, one immediate question you might have is this is fine, but how ill-posed is this problem? It turns out, in fact, that NMR spectra are incredibly unique. Right? So if you take kind of all possible geometries that you might generate for a particular molecule, here's just a subset for C6H10O2. Right? It actually looks like almost like a hash function, right? Kind of like a little barcode. And you can brute force through this space. These are the carbon, all the possible carbon spectra. These are all the possible hydrogen spectra for, again, one type of molecule. And you can look at those differences. I won't go through these metrics here, but the takeaway is that they're all bounded away from 0. That is, that it does appear that there's actually no collisions here. And you might say that's fine, but maybe it's like a normal hash function, and you're just kind of doomed. But the reality is there tend to be patterns in these spectral frequencies. Right? So if you look at different little environments around a carbon, say here, the resulting frequencies tend to cluster. They tell you something kind of distinct about that local environment. And in fact, if you brute force through all possible things that you can bond with a carbon, right, you get this kind of nice picture of possible unique structures. So let's think about how to use that. Going back, we have some molecular formula. We have some spectrum. We're trying to recover the structure. Right? That is, we have vertices and per vertex properties, and we'd like to uncover the edges. Now, this is an inverse problem, right? We have some system, we have a measurement process, we have some data, and we want to go in the opposite direction. Now, the concern here is that maybe this forward model isn't terribly well understood. And in fact, the reality is, to approximate to this forward model is hard to compute. Right? So we'll go through a brief tour of what are called ab initio methods. So this is, if I give you the structure of a molecule, how do you compute its spectrum? And again, we're going to use a common drug that many graduate students abuse. The process to simulate a molecule's spectrum from its structure is very challenging. So you start with Advil here. First, you have to figure out all the three-dimensional conformations of that molecule. And then you have to run a bunch of quantum mechanical calculations to compute what these spectra are. And these things are very slow, right? You then get one for each conformer. You have to weight them accordingly, and finally you get out the spectrum. But the point here being that to generate this data, our forward model here is actually incredibly computationally intensive, right? So there's actually a cubic term here. We're kind of down near small enough molecules that it doesn't really show up much. But we start getting to the point where to simulate the spectrum for a single molecule takes kind of 40 core hours at a certain level of theory. So instead, we're going to go, and so that's too long for the kind of deep loco style approach we were talking about. So instead, we're going to try and learn a fast approximation of the forward model for some relatively low quality user submitted data. Right? So our approach is going to be to start by approximating this forward model. We'll talk about the inverse problem later. In particular, it's ongoing work, but we've made kind of substantial improvements over the past few months, which is exciting. But let's talk about first how to approximate this forward model. We're going to use some great results from deep learning recently in the area of graph neural networks. So there's a lovely review that I can point you to from some friends at DeepMind. But the idea behind graph neural networks is that what you want to do is learn a bunch of local graph filters and kind of convolve them over the topology of the graph, right? And you'd like to stack those the way we've gotten used to stacking things when we do deep learning, right? Such that at each level, you're perhaps capturing a larger fraction of the local environment. And we're going to use that then to kind of start with the topology of the graph and some per atom features, and ultimately predict a mean and a confidence level for each atom's frequency, right? So we're going to try and go, and from this collection of experimental data that we have, learn to predict those resonance frequencies with a confidence number, right? So you can think of this as we're effectively fitting a variational approximation to the posterior. Now, I obviously wouldn't be showing this if it didn't work. So this is the reconstruction error for hydrogen and carbon, right? Both the mean and the worst case. But I think the more useful way of contextualizing that for people who aren't chemists is to compare with existing methods. So there's this technique called House codes, which are a machine learning technique used to predict these resonances, developed over the past 20 years. But there's also these ab initio techniques. So we're going to do something a little crazy here. We're going to obviously compare to the old machine learning methods, but we're also going to compare to the best-in-class physical methods that we know, right? So let's actually exploit what we know from physics here and try and run these systems forward, right? And we'll compare what our empirically derived function produces to both of these methods. Now, why are these methods not perfect? Well, of course, all of physics is fundamentally an approximation. And there are many approximations that you have to make and pick when doing these sorts of things. In particular, like the solvent model matters. Remember, we're not actually measuring an individual atom or an individual molecule, but it's living in some sort of liquid where there are interactions. So let's see how we do. So we find that our ability to accurately predict these chemical shift parameters is, for both carbon and hydrogen, is obviously beyond what we were able to do with existing machine learning approaches, but is actually more accurate than our best physics-based models at this level of theory. And we can kind of tease this apart for kind of different bonding pairs and these sorts of things. And all error bars are bootstrapped 95% confidence interval of the mean. But the takeaway here is that we think that kind of we're robustly doing a better job than our ab initio physics at predicting what these spectra should look like. And what this means is that at the end of the day, we have a system that for very fast and accurate estimation of chemical spectra, right? So the ongoing work here, and don't worry, this is I promise we're going somewhere with this, right? We'd like to incorporate richer molecular structure, right? We'd like to be able to do even better than this. And we'd like to be able to predict some of those additional quantum coupling parameters. Didn't really talk about those. And you can even imagine trying to kind of combine our ab initio data, right? So the forward simulation data that we have from the supercomputer simulations with carefully made experimental observations. But we're not going to talk about any of that right now. We're going to go back to our inverse problem, right? So now we have the ability to generate kind of an arbitrary amount of data, right, through this approximate forward process. How do we go in this next direction? Well, immediately, if I say I'm going to observe something, and then I'm going to compute some graph from that, immediately there's this question of isomerism, right? So immediately we have to be able to ask the question, are these two graphs the same? This is kind of I'll say, classically hard problem, and very much shows up in this case as well. We're going to sidestep that issue a little bit. And in fact, instead of trying to predict the entire graph the way we did with something like Deep Loco, we're going to treat this as a sequential bond formation problem, right? So I'm going to start with some collection of atoms. I'm going to say, these are the atoms I know that are in my molecule. I have no idea how they're connected. And I'm going to try and guess the first bond I should put down. And then I'm going to try and guess the right next bond that I should put down. I'm going to try and sequentially build this molecule up, right? A bond at a time, until I recover what I think is going to be the correct answer, right? So what do I want here then? Well, what I really want is some function that's going to give me the kind of the distribution, let's say, of possible next bonds conditioned on the existing bonds. We'll call that the state of our system, S of k, and the observed spectrum, right? Those observed per vertex properties. So we've structured this as a Markov decision process. Is this easy or hard? Well, you might argue that it's easy, because all of our states are fully observed. And you might argue that it's easy because all of our actions are clearly deterministic, right? There's none of the noise that shows up in kind of traditional MDP type systems. But this is hard partly because we only can accurately estimate that spectrum at the end once the molecule is all kind of wired up, right? In particular, those ring structures that show up dramatically change the resonance properties of the molecule, right? So our ability to ascertain how well we did is delayed into the future. Additionally, remember, we know something about the local structure, but we still don't really know how unique these spectra are. So we're going to treat this as an imitation learning problem, right? See, we're going to start off with this per vertex data, what the atoms are, right, what their valence is, what the observed frequencies are, and some existing bonds, right? And we're going to say, what is the right next bond to place? Oops, right? What is that right next action? we're going to do this. We're going to basically use a deep network. The exact mechanics there, I think, are a little bit irrelevant. But our training data is going to be a bunch of partially assembled molecules and a list of all valid next edges that they might place, right? So at each point in time, we're going to compute any of these edges which of any of these edges are possible valid next edges. And then we're going to train this in a supervised manner, right? What this means is that we can basically figure out how to put molecules together by giving lots of examples of molecules that we've kind of taken apart in reverse. Now, will this work? Now, last time when I gave this talk, that's basically where we were, right? Now we've started to try and quantify performance. All right, so we're going to start with a collection, an existing kind of benchmark set of chemistry molecules. We're going to use our forward approximation, that thing I was telling you about earlier. And we're going to train on roughly 100,000 of these molecules and kind of validate on 10,000 of them. And we'd like to figure out how many of these molecules do we perfectly reconstruct with this imitation learning approach. Right? So if we just greedily run that process forward after training for a few days, right, we can perfectly reconstruct 14% of the molecules. But if we embed this in a backtracking search, right, we find that, in fact, we can perfectly reconstruct 46.7% of the molecules. Right? And by perfect, I mean every bond and every atom are correct. Now, if you had told me the last time I gave this talk that this is where I would be now, I would not have believed you. So this is, I think we can go even further. So the question is how? How do we improve performance? Well, this goes back to the question Sean was asking. See, our training data starts with a valid molecule and randomly deletes edges in some fashion. That induces a distribution on graphs, right, on those states, which I'll just kind of cartoonishly show here. But as we're putting together these molecules, our network is going to be putting together the molecule in a way that will potentially look very different, right? It has no real way of understanding that these two distributions, are different. So we have this kind of distributional shift. But fortunately, some people have built algorithms that tend to be fairly good at compensating in an imitation learning setting for this sort of distributional shift, right? And Dagger is the kind of canonical example here of these sorts of approaches where the idea is that you find places where your algorithm has made the wrong choice and throw that back into your training data set. Now, there are people in the audience, including Kevin, who I think are very skeptical of the long-term, what you might be able to say robustly about whether or not Dagger works. But I think in practice, especially for these sorts of things where I effectively have an infinite amount of training data, it's likely to work, and we've seen some, just over the past few days, improvements there, right? The idea being that we can correct for this distributional shift in some sense online, and hopefully get that 47% number up to, I want to be at 100%. My collaborators tell me that might be greedy, but I think we can get there. So we've been talking a lot about both approximating the forward model and kind of trying to invert this problem. And I think we can increase this reconstruction accuracy by correcting for a lot of this distributional shift. There's still a lot of work to go in that this abstraction that we're using of molecules as graphs is really only an abstraction. It's a pretty good one, but there's a lot of existing interesting structure in molecules that we'd like to take advantage of, right? And of course, this reconstruction process right now takes about 2 minutes per molecule, and I'd like to be able to get that up. So we've talked about these two kind of structured inverse problems, right? And we've talked about basically this inference part here. But let's talk about where to go from here. I think there's a real opportunity then to think carefully about ways we can use more advanced forward models in instrumentation and measurement. Think about how do we do hardware and software co-design, right? Most of the equipment that we're talking about here has kind of been designed to produce results for human consumption. But if we have full control over both hardware and software, maybe we can do better. And there's even an opportunity here for active learning style techniques. So let's talk about richer forward models, right? The opportunity here, this is a very complicated microscope built by a very industrious graduate student. But wouldn't we like to be able to do this kind of instrumentation on substantially cheaper and less precise hardware, right? I think there's a real opportunity if we can capture the things like the nonlinearities or the imperfections in our forward simulator, we should be able to do this kind of reconstruction. I think there's a similar opportunity to combine ab initio techniques from a variety of physical systems, right? Ranging from kind of molecules that we're talking about to some work that we've started exploring on using electromagnetic simulations for measuring very small objects. I think then there's a whole host of other experimental techniques like novel NMR techniques or mass spectroscopy that we can potentially incorporate into our forward model. Then there's this issue of co-design. So this here is a schematic of what a microscope actually looks like, right, for these super resolution tasks. And you can see there's kind of this 3D volume over here on the left, and there's some optics, and then you get a camera on the other side. But what we've done here is insert this special physical device here called a spatial light modulator that lets us vary that point spread function. So we can engineer the system response of our microscope, and we can engineer this recovery algorithm. And so we're starting to look at ways of jointly optimizing both that system response and that recovery algorithm, right? Of doing kind of adaptive filter design here, or co-adaptive filter design. This then becomes, I think, very practical for NMR as well, right? So when people traditionally talk about NMR, this is the way you present it to undergrads. We say, well, there's some excitation pulse, and then there's some ring down. But the reality is the way we excite these systems in the real world is substantially more complicated, right? People are trying to hand engineer all these pulse sequences to tease out little aspects of the molecule. In fact, Ray Freeman has this lovely book about this that he calls spin choreography, talking about how you might try and kind of choreograph all of these spins to elucidate the interesting information. But the reality is we're still doing a lot of this by hand, and I think there's a real opportunity to both optimize and then do joint optimization and recovery. Finally, I want to end with this question, right, of what is a robot? Because when we think about robots, we think about things from fiction that may someday be governor. We think about industrial automation. We think about dynamics in the real world. And we sometimes even think about things that we as humans can't even do, like flight. But I'd like to encourage everyone to think about robots a little bit more broadly. Because the reality here is that at UW, I'm sure you have at least 1,000 robots within a mile of where I am. But they take the form of spectrometers, or of magnetic resonance imagers, or the form of flow cytometers, or of microscopes. Right? The reality is that every piece of scientific instrumentation that exists today is controllable via code. It interacts with the physical world. It has a model of that physical world that maybe it believes, maybe you believe. And it's producing data. And so as computer scientists, we can be involved in every single one of these measurement modalities. There's a real opportunity here, right? And if we project forward what this might even look like, right? Imagine if for this microscope, instead of just doing co-design, we started taking specific measurements and then engineering the point spread function in real time, right? What if we tried to build active instrumentation that itself reasoned about the prep under study, right? I think for NMR, this becomes especially powerful because, as I talked about, the signal is actually very signal and noise ratio limited. But there are these rich quantum dynamics that we can exploit. And of course, making NMR measurements is hard for the physical hardware, right? There's kind of all these questions about homogeneity and sample sensitivity and all of that. But this is fundamentally a system identification problem of the kind that we've been thinking about in computer science for a very long time. I think there's a real opportunity here. So mostly today, I've talked about kind of ways of applying various structure prediction techniques to some of these inverse problems. But I really want people to think about as we go forward in computer science, as we think about kind of what it's going to mean to do computer science and even data science over the next, say, 20 years. How are the opportunities that we're creating for kind of modeling and inference and scale going to impact all these other parts of science that we care about? And with that, I would like to thank all of my collaborators, many of whom did most of the real work here, and open it for any questions.
Any question?
Yes.
So for your first example of microscopy, you talked about how you have this assumption that your signal is sparse. And I was wondering, so when you used this neural network, how did that take advantage of this assumption of sparsity?
Great. So the question was, how does the neural net kind of exploit the underlying sparsity in the system? The way we have that, the way that works is in fact, we only let the neural net output some fixed number of points, k. Right? So those weights that we said that measure point intensity also serve as our filter for was there a point here or not, right? So in some sense, and this is actually an interesting place where we could test, but to Shyam's point, but we didn't. All of our training data was relatively sparse. We varied the density tremendously, but we never kind of, including up past that 256, where we know it's going to make errors. But we never vary it kind of to insane levels, right? That's totally a thing we should have tested. But that's kind of where the sparsity comes in. The loss function, and in fact, the network itself is kind of designed just to output discrete sparse sets of points. Does that answer your question? Yes.
Thank you very much for your talk. It's very interesting. One question I had in relation to microscopy application application too is there's a deep parallel here to astronomy where you have an image that's say a telescope image, and then you're mapping to a catalog of stars, and we have access to a point spread function. And there it seems like what a lot of people are doing these days is they come up with some forward model with the PSF, and then they just sample directly from the posterior using reversible jump Markov chain Monte Carlo. And one advantage there obviously is you have fully marginalized uncertainties, but a disadvantage is it's very slow. And so my question for you is that the trade-off that you're looking at here when you directly model this inverse function, that it is just very fast, but you might lose out on other aspects like that?
Great. So I've been working with astronomers at Berkeley on this very problem. I think there really clearly is this kind of trade-off in terms of inference speed versus kind of capturing posterior uncertainty. Lots of people work on like Bayesian neural nets, but like it's very bleeding edge, let's say, right? But the other appeal for at least this application is that we can turn the density up on our forward model in a way that what we're actually getting very good at is kind of disentangling overlapping clusters of points, right? Which for a lot of the fitting methods I've seen in astronomy, there's kind of the assumption that you're just trying to do a good job of localizing a single emitter, right? Now you can construct that into your model, right? And do more reversible jump and these sorts of things, but it's hard, right? I do think that if you have a fully Bayesian method that you believe works, and it's like within your performance envelope, and you care about uncertainty, you should totally do that. Never would I suggest anyone not do the proper Bayesian thing, much to perhaps my advisor's chagrin. But especially for these sorts of microscopy applications, where at the end of the day you're going to try and localize 1,000 frames of this data very quickly, I think there's a real appeal to kind of directly approximating this inverse function. What I'd like to do is be able to have some notion of uncertainty, right? Like if you're a grad student or and want to work with me, please send me an email, because it's important for a lot of these science applications and very hard to uncover.
Right. So I guess this is more a question going back to this robustness. Like this example of controls, you could say, look, we could ignore like model predictive control and go to building a way of approximating the inverse function. But then if you kick the system, it just falls over because it's very bad, outside of the domain you're testing on. And like, how do you get a sense? And somehow just checking on some standard distributions seems like a reasonable thing to do. But if we're really going for scientific discoveries, like how do we look at the ways to kind of probe where you're failing to get the approximations correct, as opposed to just using the physics or give a sense of like.
So the sorts of, forgive me for calling them this, adversarial examples we've tried have included things like where we increase the point density really high, or we start putting points close together and see if that, so kind of things that we would not generally expect to occur in the real physical system. But I don't think there are, I mean, the challenge here in some sense, and I think we alluded to this at lunch, is that I don't have the kind of robust mathematical guarantees that I would get out of doing the kind of MPC equivalent here for performance for the system operating outside its traditional bounds, right? So if I were using, say, a perfectly created, the traditional forward model approach, right, where then I solve the resulting thing, and I double my resolution, right? That's a thing that's extreme, you just change some constant in your code and it's all probably going to work fine, right? Here, I have to like train a new network. Who really knows what the network's capacity is going to be for that sort of thing? Is it going to work? Is it not? Well, I guess we're going to have to go to these empirical measurements again. So there's a real kind of trade-off there, right? On the reason why the applications I've focused are either kind of a place where speed is a real rate limiting factor, like on these new microscopy sides, or where we just don't have good ways of doing it, like on the spectroscopy recovery side, is that to the point I made earlier, I think if you do actually have a good kind of inverse approximation, for example, like on the MRI side, you should just, or inverse solver, you should just be using that.
Well, I'll take the last question then. In these spectroscopy examples, you had one chemical, a clean chemical isolated alone. You were trying to do the inverse problem of you just saw the spectral lines and trying to get the chemical back. Well, I mean, is this very realistic? I mean, do you usually have these clean signals here, or is it more like the sun when the discovery of helium, where you've actually got a bunch of different chemicals or atoms in the same space in a superposition of them? And can your methods have any hope of recovering a superposition of molecules? Great question. So for most of the natural product structure elucidation work that people do, you actually generally have, like, by far one substance in
in your experimental vial, right? In fact, that's a thing that chemists have gotten very good at doing, right? That said, there are many other interesting applications, including this field of metabolomics, which I'm interested in, where you do have a mixture, right? And where you want to be able to uncover this mixture. Now, the methods I've talked about here make very strong assumptions about kind of what the structure is, like how many molecules there are, what the atomic various elements are, and what their ratio is, and that sort of thing. The mixture problem is much more interesting, but for many of those mixture problems, often the mixture that you're trying to figure out is some finite set, right? So there might be kind of 800 metabolites I'm interested in figuring out the relative concentrations of, and I know that set ahead of time. And there, I think there's a real opportunity for kind of these sorts of methods to work because you're not trying to do the structure discovery problem, but instead just do this unmixing. But I think we're still a ways away algorithmically from being able to make heads or tails from a mixture of completely unknown substances. Would love to get there.
Let's take the speaker again.